A single rifle round carries enough kinetic energy to pass through a solid inch of ordinary glass. Yet ballistic-resistant glazing, sometimes not much thicker, absorbs that same energy and holds together. The difference isn't thickness. It's a precise architecture of transparent layers, bonded under controlled heat and pressure, where every material serves a calculated engineering role. And that engineering begins long before the first sheet is ever stacked. Standard safety glass is engineered specifically to mitigate accidental impact injuries. Tempered glass, treated with rapid thermal cooling, increases mechanical strength to fracture into small, blunt cubes. Laminated safety glass uses an interlayer to hold these fragments together during a collision. Neither category possesses the capacity to stop high-velocity projectiles. Ballistic-resistant glazing must manage forces orders of magnitude greater than an accidental strike. This performance is impossible to achieve by simply increasing the thickness of a single sheet. Instead, it requires a balanced composite system where successive layers deform, erode, and capture both the projectile and structural fragments on the protected side. Ultimately, defensive capability belongs to the complete, evaluated assembly rather than the generic concept of bulletproof glass. The cross-section of a ballistic panel reveals a highly structured composite where each material performs a specific physical role. Rigid glass layers on the strike face provide extreme hardness and stiffness, initiating the deceleration and deformation of an incoming projectile. When this front layer fractures, it absorbs the initial kinetic energy while transferring the remaining load to the interior. Bonding these glass sheets together are transparent polymer interlayers. Polyvinyl butyrol, or PVB, is widely used for its optical clarity, strong adhesion, and ability to hold shattered fragments in place. For designs requiring higher structural stiffness, ionoplasts offer a more rigid interlayer response. Polyurethane and thermoplastic polyurethane, or TPU, serve as flexible alternatives when extreme temperatures or high elongation capabilities are required to maintain bond integrity. On the protected side, ductile polycarbonate acts as an energy-absorbing backing, flexing to capture lingering debris and prevent dangerous spall. Ultimately, whether an architecture relies on all-glass laminates, glass polycarbonate hybrids, or polymer-heavy designs, these configurations represent distinct engineering pathways rather than a simple hierarchy. This precise sequence of layers is defined by strict specification sheets, establishing the blueprint for the manufacturing phase. The manufacturing phase begins by translating engineering drawings into physical components. Each incoming glass slide undergoes strict dimensional checks, measured against tolerances as tight as plus or minus 0.1 millimeters. An acceptance standard for standard commercial glazing is insufficient here. A security laminate requires far more stringent parameters. Inspectors examine every sheet under polarized light to identify stress concentrations, microfractures, and surface scratches that are invisible under normal lighting. Once verified, the sheets undergo a multi-stage wash with deionized water in an ISO Class 8 cleanroom. Dust, grease, and moisture represent immediate production risks. Even a microscopic speck can compromise polymer adhesion or create an optical defect. During layup, technicians position the clean glass and polymer sheets on an alignment table in the exact sequence specified by the design blueprint. Alignment fixtures prevent the layers from shifting. Handlers document batch numbers and material certificates for every individual ply, establishing a complete traceability record for the finished panel. At this stage, the assembly is merely a loose stack of parts. Transforming them into a unified composite requires controlled consolidation rather than simple adhesion. The stack is sealed inside a silicone bag and a vacuum is pulled to evacuate the bulk air trapped between the solid layers. Next, the panel enters the autoclave, where uniform heat and pressure are applied simultaneously. For standard PVB and ionoplast interlayers, the processing window typically ranges from 135 to 150 degrees Celsius, with pressures between 10 and 14 bar, though these exact parameters depend on the specific material supplier and equipment. Thermoplastic polyurethane, or TPU, requires an entirely different thermal profile. During the high-temperature soak, the polymer interlayers soften and flow, filling any micro voids and creating a uniform chemical bond with the glass surfaces. In the autoclave, uniform pressure is everything, notes lamination engineer Thomas Vance. If the pressure or temperature fluctuates even slightly during the soak or the cooling cycle, the polymer won't flow evenly, and the layers will eventually separate under stress. A slow, programmed cooling phase prevents the development of residual thermal stresses that could cause optical distortion or delamination. All cycle logs, temperature sensors, and pressure records are preserved to document that the entire process remained within its qualified operating limits. The cured composite is handled as a finished component. Abrasive water jet cutting performs high-precision cold contour shaping without introducing thermal stresses that could micro-fracture the edges. Straight borders undergo precision, CNC grinding, polishing, and beveling before technicians apply a protective polymer sealant or bond a structural metal flange to the exposed perimeter. This edge treatment acts as a critical barrier against moisture ingress, framing stress, and eventual delamination. At the quality control station, a specialist conducts a precise hands-on demonstration to verify the finished panel's physical dimensions and structural integrity. Using an ultrasonic probe, the specialist maps the total thickness across the entire surface and scans the interior layers for hidden bond discontinuities or microscopic voids. Luminous transmission and haze, defined as unwanted light scattering, are quantified using a spectrophotometer compliant with ASTM D1003. Automated imaging systems map any minute optical distortions, while high-resolution sensors check the finished beveled edges for microchips or incomplete seals. Every measurement is entered into the factory quality log, where the final decision to release, rework, or reject the panel is recorded. Independent testing laboratories receive these production specimens under a strict chain of custody, verifying each panel's dimensions, thickness, and layer configuration against official blueprints before testing. Certified evaluations rely on standardized, calibrated procedures. Architectural glazing is assessed under UL 752, while European applications conform to EN 1063. For transparent armor materials, NIJ 0108.01 serves as the reference, though it does not define framing or mounting conditions. During the test, a projectile is fired at a specified velocity, angle, and shot pattern. Chronographs measure the exact impact speed, while high-speed cameras capture deformation and fracture propagation. Behind the specimen, backing materials and fragment collectors measure physical deformation and catch any ejected spall from the protected side. Factory quality records document process consistency, explains laboratory testing engineer Sarah Jenkins, but independent certification is a performance statement. Our final report is tied to the exact construction, material layers, and mounting configuration validated during this controlled procedure. Following the impact, a post-test examination checks whether the laminate behaved as specified, ensuring the layers remain bonded and that no fragments or projectiles penetrated the safe side. The laboratory's final report certifies only the exact composite design tested, providing the objective performance baseline required for secure architectural and transport applications. Translating a certified panel into a real-world installation requires balancing environmental, structural, and optical trade-offs. A configuration optimized for a vehicle cannot simply be transferred to a building. They operate under entirely different physical constraints. Mobile armor must withstand constant road vibration, wind loading, and frame flexing, requiring lighter, curved, polymer-heavy designs. In contrast, fixed installations prioritize large flat spans with exceptional long-term clarity. Engineers evaluate these choices using 4 baseline parameters: layer construction, relative mass, optical considerations, and typical application context. Glass-dominant designs provide highly durable, scratch-resistant surfaces with excellent long-term optical quality, but their massive weight demands heavy-duty structural framing. Conversely, polymer-rich architectures utilizing thick polycarbonate cores significantly reduce structural dead load, but they introduce vulnerabilities to ultraviolet yellowing, surface scratching, and edge seal degradation over time. Ultimately, specifying a ballistic system requires aligning the precise material composition with the structural framing, environmental exposure, and threat level of each specific project. Today, transparent armor remains a dynamic frontier of material science. As threat profiles evolve, engineers must continuously balance molecular bonding with optical performance. In this quiet discipline, safety is not defined by raw mass, but by the precise microscopic integrity of the composite. Subscribe for more engineering insights.